a year. His PhD was from UCLA, and then he did his postdoc at UCSD. His research has been broadly in the area of kernel methods in machine learning. So that's a kind of alternative to the normal deep learning architecture, much more explainability to it, as well as generalizing machine learning models. So we are very happy to have you, Parthe.
Hello. Thanks for the very kind introduction, and thanks for hosting me. This has been a really nice experience. Okay, let's get started. My title today is Old Dog, Old Tricks, New Show. So here the dog is old, the trick is jumping through the hoop, but it's me who's jumping through the hoop. Again, I'm going to talk about fast first-order methods for training what are called kernel machines. These used to be a very popular family of machine learning models in 2010, but ever since deep neural networks picked up, they've sort of fallen by the wayside. But over the last 7-8 years or so, people have realized that they don't understand enough about deep neural networks and to actually build systems that you can trust and understand better. They've relied on kernel machines as the lens to understand what exactly is happening inside a deep neural network. And so there's been a lot of renewed interest in kernel machines as a theoretical tool, but also as a practical tool. So today we're going to focus on the practical aspects of these kernel machines. I think this is not connected to this machine anymore. Until then, I'll use this. So I'm going to jump right into math because I don't know how else. So let's start. I'm going to talk about supervised machine learning. So this slide is just to set up notation for the rest of the talk. I don't have to cover everything, and we're a small group here, so we can keep it interactive. Interrupt me if you have questions because things keep building up as we go. So we're interested, we're given n samples of inputs and outputs. Xi's are inputs and yi's are outputs. Xi's are some coming from some compact subset of RD, and yi's are some real value targets that we want to fit a model on. And the goal is to find a map from this domain to R that best fits my data. Okay, so in my view of machine learning, these functions are really the first-class citizens of machine learning. I think of data as maybe a secondary thing. And the typical way in which we will be focusing on learning this map is by solving some kind of an optimization problem. So this is a variational formulation of what is called empirical risk minimization. This is some kind of an empirical risk loss function. This measures how well your function, proposal function f is fitting your data. And then there is some sort of regularization term that's going to penalize the smoothness of or roughness of the hypothesis f that you're proposing. Okay, and we're going to look at a class of problems which are called non-parametric regression, where the simplest way to state is that the hypothesis space H here, over which you're searching your hypothesis, is mathematically precise. You've given a very nice description of what the search space is mathematically, but operationally it's quite big. You don't give me a computational algorithm as to how you want to traverse this search space and how you want to come to the solution of this optimization problem. So here is an example of a hypothesis class. This is called the Sobolev space of order 2. The domain here is d equal to 1. I'm only looking at functions defined on the 0-1 interval. These are twice differentiable functions, and we're looking at functions which are 0 at the origin. Their derivative is 0 at the origin, and this norm of the function is finite. Okay, so this class of functions is the Sobolev space. This is a vector space, and this is the description of this optimization problem. It doesn't tell you how to do optimization because this is now an infinite dimensional space, right? How do you actually solve this optimization on a computer is not very clear. We'll be focusing on a very specific type of these function spaces, which are called reproducing kernel Hilbert spaces. These are in These are basically the main object in what are called kernel machines. So let's look at them in some detail. So the definition of an RKHS is the following. For all functions f in your hypothesis space, the map that takes you from f to f of x, right? So an element in the hypothesis space to a real number, this map is continuous, okay, in the function space. And this has to hold for all x in my domain. Whenever that happens, my space, hypothesis space, is a reproducing kernel Hilbert space. Yeah.
So just all f of x is, each f is continuous, that's all.
No. I'm saying the map that takes from f to f of x. This map is continuous. The evaluation functional is what this is called. That evaluation functional is continuous. Okay, and here is one property that elements of this hypothesis space satisfy. It's called the reproducing property, which is that there exists a unique positive definite function k, okay, that satisfies this equation here. So k is a bivariate function. It takes two arguments. Both of them are from the domain, and the output is a real number. Okay, and what does this k dot x mean? This is if you fix one of the arguments, this is now a function in the second argument, right? So this is now an element of the function space again. And if you take the dot product in this function space of f with k dot x, you get exactly f of x.
What do we mean that k is positive definite?
Right. So positive definiteness is the property that if you were to take any finite number of points in my domain, okay, and I create the, let's say you take n points in this domain, you create the n by n matrix of evaluating this function pairwise at all of those points. This is now an n by n matrix. This has to be a positive definite matrix, right? So we're going to focus on these kind of kernels. Okay, so this is the abstract definition of what is a RKHS. A more operational definition is the following. The hypothesis space is the closure of the span of all such functions k dot x.
Can you give an example of such a positive definite function?
Yes, so that's the Sobolev space that I shared on the previous slide has a kernel corresponding to a unique kernel corresponding to that space. Okay, so x and z are now in 0, 1. And this is the value of the kernel function for that particular space.
Is this something coming from beta equation?
I'm not familiar with that. So maybe. I'm not sure about this. I'm not familiar with this term.
Why do we have so many 2 minus 1?
Right. So the 2, I put them as 2 minus 1 and 2 minus 1 because this you can define for arbitrary integers alpha. So the Sobolev space I described to you was of order 2, which was penalizing the L2 norm of the second derivative of the function. You can define it for arbitrary derivatives of the function. Yeah.
What is the meaning of this plus over here? Which is just
Yeah, the plus is sort of a ReLU, which is you take the positive part of the, it's 0. Yeah. Yeah. Okay, so we are going to work with non-parametric regression problems in an RKHS. Okay, and that's what I call the old dog. So if you were to look at a non-parametric regression problem in an RKHS, so H is now a special hypothesis space. It's a RKHS. It has more structure than a generic function space. There is a nice result that goes back to the 1970s, which tells us that any optimal solution to this optimization problem has this form. Okay. This seems quite non-intuitive, but it's essentially a fancy version of Pythagoras theorem. There is the proof is really a 2-line proof. It's not even worth going into. But this now reduces the search space from an infinite dimensional space to a finite dimensional space. So now these are sort of basis functions, and now I need to find what are the coefficients of these basis functions.
So this k is the k that you choose.
The k is the k. So the k corresponds to the k that is generating the RKHS.
K is great.
Is unique. Yeah.
It's unique.
Yeah.
How rich is this HK? In one.
It's quite rich. It's quite rich. Essentially.
Any universal approximation kind of theorem?
Yes, there are those kind of theorems as well. And in fact, the study of a lot of what we understand about neural networks is by mapping it to a corresponding RKHS. Yeah.
When you get the operational definition, doesn't it say that any F can be written in this form?
Okay, so there is one caveat here. So here the X's were spanning over the entire domain, right? Whereas here the Xi's are spanning only over the training data Xi's. Okay, so this is a finite n-dimensional subspace of the RKHS.
What does my simple X represent here?
Sorry?
What does my X represent here? I understand Xi is the training.
X is now my argument. At test time, you would want to make a prediction on some other arbitrary X that is in your domain. That is this X here. Yeah. Okay. In old courses in machine learning, they used to teach this thing called a kernel trick, which was basically converting all things related to linear regression and linear classification into non-linear regression, non-linear classification. It's a very elegant theory. It very cleanly tells you how to think about non-linearity while still using tools from linear algebra. And this is what really got me into this area, the connection to deep learning. And there is this nice family of kernels called the neural tangent kernel, which tells us what's happening in the function space when training is happening in a neural network. Okay. There's also another line of work I have been pursuing, which tells me how I should be choosing k, the function k. By looking at data, how should I choose the k that gives me the best performance on test data? Right? That is another line of work. Today, I won't be talking about that. I'm going to assume that somebody has given me a positive definite k, and I'm going to work with that k and do the training algorithm and see the complexities that arise in that. Okay, so we're going to talk about how to efficiently solve this once k has been fixed. So once you fix k, there is an equivalent RKHS also that you fix. Okay, so there is this one-to-one correspondence, and that's what we're going to exploit today.
Yes, I still this is linear regression.
Right, so this is linear in alpha, and yeah, so it is in some form it is a type of linear regression. Yes.
No, because if k is fixed and I have n data points, then my coefficients k, x, x are
fixed.
but x is varying, so it's not.
So it's linear in the parameters, it's non-linear in the input. Right? When you study linear regression, you always think that linear regression is about linear functions. It's not. It's about functions that are linear in the parameter. Yeah. By the way, till what time can I go? 2:45. Okay. Okay. So let's now look at these things. So we've seen the old dog. Now let's look at the old trick and how kernel machines have been classically trained until 2 years ago. Okay, the standard way was you have to solve this sort of minimization problem in the Hilbert space. You apply your representer theorem, which tells you that your optimal solution is actually f parameterized by alpha. Okay, and then you convert this into an optimization problem over Rn. Okay, and because n is large, you can't use second order methods. So you typically use some kind of a first order method, maybe something like gradient descent. There has to be a gradient here. And you optimize over the coefficients alpha directly, and whatever you get in the end, your final proposal is f alpha, alpha being the solution to this optimization problem. Yeah, is that clear? Okay, so let's look at an example. In the case of square loss, you're just minimizing this sort of squared error, right? And now if I were to plug in the form of my kernel machine, this reduces to minimizing this sort of objective function. This is a quadratic program, convex quadratic program in alpha. And if I were to write the gradient descent for this, it's going to look like this. I have kxx transpose times kxx alpha minus y, right? And you can also write a stochastic gradient descent version, which looks at only a mini batch of your data, and you get an update which looks like this. Note that in the SGD, when you do it this way, you have to update all the coefficients, even if your batch size is just 1. Yeah. So here are sort of a laundry list of desirable properties that I want from any algorithm that I will design to train a kernel machine. I would want to handle arbitrarily big data. So my data could potentially be infinitely large, and I should still be able to train this efficiently. I would want to do this in a matrix-free manner, which means I don't ever want to store any kind of kernel matrices. I only want to calculate these kind of forward passes through my kernel machine. And I want the training to be batch friendly, robust in the sense that it's stable to low precision as well. And I want to use the resources well, right? Importantly, it has to work with any kernel. So there are some techniques in this that allow me to use the special structure of the kernel function. And those are sort of bespoke methods that are developed for every individual kernel. But I want to develop things like PyTorch, which are generic. They just work for any kernel function that you give me, right? There are some sort of classical algorithms people have been using. Things like conjugate gradients. They're not very stable in some sense. They have some stability issues, and coordinate descent algorithms. These are extremely hard to analyze, and the kernel matrices are extremely ill-conditioned, and that's what makes these algorithms not so nice to use in practice. Okay, and so we want to take a fresh look at this problem, and that's where we came in. And here is what our proposal is. So you have these two devices here, which is the representer theorem and your first order method. And we are just going to reorder these and see what's going to happen. Okay, so the approach is going to be the following. You have this optimization problem in the Hilbert space. You apply a first order method to that optimization algorithm. So something like gradient descent, right? This is actually just an algorithm on paper, because I can't really implement this algorithm, right? This is in an infinite dimensional space. And then I'm going to use the representer theorem, which tells me that, well, my solutions are always going to lie in this kind of a finite dimensional subspace. So maybe I just need to track what's happening to this trajectory in that finite dimensional space. And that's what gives us a new family of algorithms. And we're going to go through some of what those algorithms look like. So I want to run these dynamics, okay? And I know that my function is of this form, okay? So is there an update equation in alpha that actually tracks this dynamics in the Hilbert space? Yeah. All algorithms guarantees in optimization typically are specific to the dynamics, right? So it depends which space you're doing the dynamics in. So here the dynamics were happening in the Euclidean space. Here my dynamics are happening in the Hilbert space. Yeah. So this is a sort of philosophical difference also in how we're going. We'll see. This ends up changing the entire game quite a bit. Okay. So here is a quick trailer of what you're going to see. Until 2022, Falcon was sort of the state-of-the-art algorithm, and it could only handle about 500,000 samples. Okay, for 1 million samples, it would go. It would run out of memory, because the memory. It was a really memory-hungry algorithm. It required something like 4 terabytes of RAM to fit a model with 1 million data points. It's the name of the method is Falcon.
The ideas are what you shown. Like the idea was to...
No, so Falcon is based on this approach, whereas these EigenPro algorithms are based on this approach, this new approach that we are proposing. Okay, and so Falcon was not able to handle big model sizes or big data sets. So we came up with an algorithm, EigenPro 3, which was able to handle big data sets, but it took forever to actually run that algorithm. So it was a very inefficient algorithm. So this was an ICML 2023 paper. And then just last week, we had an acceptance in NeurIPS, which is basically a clever, maybe a careful bookkeeping of what's happening under the hood. And that actually allows us to cut down the cost quite drastically. And we go from 10 days to 21 minutes just by careful bookkeeping. Yeah.
Can you go back to the previous?
Yeah.
Yeah. In this slide, you mentioned the lower algorithm is like only there on the paper because your space that you're training over is like infinite.
Correct.
So like, and then you said in the next slide that EigenPro is based on this one.
Correct. I'm going to tell you how I'll do it. Yeah. This is just a trailer.
Okay.
Yeah. Okay, so I'll actually talk more about what this 700x means. This is actually not a fair description. There is actually something deeper happening that gives us this speed up. Okay, so the first act is going to be just traversing through a RKHS. We'll see how to actually traverse. We'll do some warm up, and then we'll develop on top of that. This is one of my, well, not one of my, this is my favorite book. It's Leuenberger's book on optimization by vector space methods. Yeah, everybody should have this book. When I moved from the US to India, all my books came in my check-in baggage, but this book was in my backpack. Yeah, it's a religion.
Optimization, but in vector space, not in the Euclidean space.
Yeah. Okay. So yeah, this is basically chapter 2 of this book, how to traverse through an RKHS, and we're going to see some fundamental tools that we need to do this. So our toolkit is going to be the following. So I'm just going to introduce some notation here. So K dot capital X is, you can think of this as an operator that takes a vector in Rn and gives me a function in the Hilbert space. Okay. And the definition is as follows. So K dot capital X alpha is essentially K dot xi alpha I. Right? So alpha was my vector of coefficients, and I get a function when I take the linear combination of my individual basis functions. Right? I'm going to use this subscript b to indicate a subvector of a big vector. Right? And when x is a set, I'm going to use the subscript b to indicate a subset of that set indexed by b. Right? And I'm also going to use this f of xb is the evaluation of f at all elements in xb. Right? So f of xb is also size of b dimensional vector. Yeah?
Because f is a real map.
F is a real map, correct. Yeah.
So can you repeat how does B come into the picture?
So B is some subset of 1 through n.
Okay.
Okay. This is just some notation I'm introducing to make my life easy to explain what's happening. Okay. This is going to be one of the MVPs of today. The Frechet derivative. This is the generalization of gradients in vector spaces. Okay. So you
XP over here is just a set.
XB is just a set of size B elements. Yeah.
It's not a set, you're saying it's a tuple which you have.
Yeah, this is a vector. So yeah, I'm just defining it this way. Yeah. Okay, so the Frechet derivative is defined in exactly the same way you define gradients. You take a perturbation in the direction of h of size t for any functional j, right? J maps from h to r, right? And I take the limit as the perturbation size t goes to 0. What I get is the Frechet derivative dot product with h, which is the direction of my perturbation. Yeah, and this is defined for all f and all h. Right. So if you notice, the Frechet derivative is an element in the RKHS itself, right? And the Hessian is a map from the RKHS to the RKHS. Yeah. Okay, so here is a warm up. So if you were to take the Frechet derivative, so gradient f is how I'm going to show these derivatives. The derivative of half of my square loss is by chain rule. I get 2 times this, which is just f of xi minus yi, the residual, times the Frechet derivative of f of x. So f of x is a real number, and I want to take the derivative of that real function of f. Right. So what is that? If you remember, the reproducing property was that f of xi is the dot product of f with k dot xi. Right. So this is just a linear. This is like the gradient of A transpose x is A. Right. That's exactly this line here. So the dot is so this is a function now. Right. This is a function. So dot is sort of a dummy variable. Yeah. No, f of xi is a scalar. So xi is some xi is an element in my domain. Xb is sort of this set of elements in my domain. Yeah. Okay. So now when I have the square loss, which is the sum of the loss on n samples xi yi, this is nothing but the residual on the ith sample times k dot xi. That's going to be my gradient, right? And using the notation that we just saw, this is nothing but k dot capital X, right? This is this operator here, right? Times the residual, which is fx minus y. Yeah. This was the full gradient, or what is the batch gradient. You can also define a mini batch gradient, which is you take a, I'm going to denote mini batch gradients with a tilde on top, right? So now I take a batch indexed by b. I do exactly the same operation. I calculate the residuals and then multiply by the corresponding basis function k dot xi. And this is exactly this k dot xb, f of xb minus yb. So this is the residual of f on my batch. Yeah. Okay, so let's start by tracking stochastic gradient descent in the RKHS. Let's see what this is going to look like. Okay, so I wrote down in the first, so I want to track this, right? And I'm going to represent f by f alpha, which is k dot x times alpha, right? So the LHS is just this, right? This f here is just this, right? And you just saw that the stochastic gradient was exactly this, k dot xb times the residual on xb.
Very stupid.
No.
So
right.
we are when we are representing f by f alpha basically.
Uh-huh.
So are we not doing the same thing as like the representer theorem before and the first order method afterwards?
No, because the dynamics are still these dynamics. I'm sort of restricting the dynamics to be on this set of functions, but the dynamics are still these dynamics. Yeah. Okay, so this is also of the form, yeah, this f alpha xb is nothing but k xb x times alpha. Yeah. And so if I actually want to track stochastic gradient descent, or one step of stochastic gradient descent, all I have to do is update the coefficients corresponding to my batch. And by how much? I should update them exactly by the residual on that batch.
Wait, why are we only updating the coordinates?
Right, because you can now think of this as k dot all of x, right? And this is only a sub vector, right? So I just put zeros in all the other parts of the vector, right? So this is nothing but k dot xb times rb is nothing but k dot x times rb and 0. So effectively, you're updating all the alphas by doing this, but you're only updating the coefficients which are not in your batch by 0. So there is no point updating them at all.
Just to understand, you basically saying I shouldn't say this divided by kx everywhere because it's everywhere. It's parameterized by alpha, so I just need to worry about alpha.
Correct.
And now xb, you can just think of zeros where it's not, and think of it as x, but just zeros where you're not in b.
Correct.
So then you can just think of updating alphas. So take out, just see how alphas are being affected, and that's exactly by what you.
Correct. Exactly. So I'm just tracking exactly this iteration. When I run this update on my computer, what I'm doing is actually just tracking this in the RKHS. Sorry? YB is the subvector of targets that I'm fitting to, corresponding to the mini batch. So here now you're only updating B coordinates, whereas if you remember earlier, you had to update all the coordinates for a mini batch if you were doing using the old show. Right? This is a convex problem. Yeah, you have fast convergence. In fact, this is a strongly convex problem because the kernel matrix is positive definite. And so even SGD converges exponentially fast for a fixed learning rate. Okay, and the rate of convergence is something like this. Okay, so F star is the optimal solution. Okay, this is the RKHS guarantee. Okay, so the norm here appears is the RKHS norm. Okay.
The RKHS norm is that second derivative.
That was one example.
Yeah, but like you can have the kth derivative contact from 0.
No, each kernel will have RKHS corresponding to that. The RKHS automatically has a norm defined for it, and this is that norm.
Kernel to an extent to give the weight to that norm.
In some sense, yes. Yeah, we don't necessarily know how explicitly, but there is a well-defined notion of that norm. That is one reason, and this is also more attractive because I don't actually need to update all the coefficients. So this is a nicer algorithm to run in practice. Right? Earlier, if you notice, there were two kernel matrices being multiplied by each other. Right? This is.
Yeah, if you had a million things, you need a million updates.
Yeah, whereas now you only have one update. Yeah.
Just to like go back, like so you're saying that the dynamic in the bigger space, when you restrict it in the representation space, that's still a convex problem.
Yes, correct. Yeah. Because of the parameterization being linear, actually. That's the reason it preserves convexity. Yeah. Okay, so this kind of is the starting point of everything we are going to derive from now. And the name of the game is exactly this. You come up with a dynamics, a simple dynamics in the RKHS, and just do this bookkeeping painfully to track how to run those dynamics in the RKHS. Yeah.
Just to understand the story, this was all understood by 2017.
The convergence was understood in 2017. The connection that this algorithm is actually running an SGD in the RKHS was not.
Oh,
that is a new perspective. Yeah. Okay. So one thing we would like to do now is precondition the SGD because the kernel matrices are really poorly conditioned. This is just how things are in high dimensions. And so you want to apply some kind of a preconditioner before you subtract out the gradient. Okay, so this P is some operator. Yeah.
This is a poor condition.
The largest eigenvalue divided by the smallest eigenvalue. In optimization, this is what determines the convergence rate. So kappa here is the convergence rate. The decay rate of this dynamics is governed by the largest by the smallest eigenvalue of the kernel matrix. And this is a very large number. And you don't want to pay this heavier price. So you want to reduce the dependence on the condition number a little, right? And so these are what are called quasi second order methods, which first precondition before you take a gradient step. Okay, the preconditioner that we are going to look at has a very special structure. It's a spectral preconditioner. So what we're going to do is we're going to look at the Hessian of the loss function, which turns out has this particular form. Okay, so this is the basis function, its outer product. So this is a rank 1 operator, and you take the sum of n rank 1 operators, and that's what gives you the Hessian. Okay. If sigma I and psi I are the eigenfunction of this operator, then you should define this as your preconditioner. This is a sort of object that comes out of numerical linear algebra in a very standard manner. What it does is it reduces the largest eigenvalue of h is sigma 1, but the largest eigenvalue of p times h is sigma q plus 1, where q is some level that you're allowed to choose. Okay, and that changes the convergence of this iteration from e to the minus t over kappa to e to the minus t over kappa q, where kappa q is sigma q plus 1 by sigma n. Yeah.
The point is condition number is the largest eigenvalue, now we want this to be smaller. So now you can make it arbitrarily small based on the values you already have in your matrix.
Correct. So you choose Q. Q is some hyperparameter you have access to. Every time you increase Q, your condition number reduces quite drastically. Yeah.
This is almost like you're removing the householder matrices corresponding.
Correct. This is exactly that. Yeah. Okay. So
Right, we have taken the tensor product of the tensor product of the H2 to H1, right? One is having two arguments over here. Is it a tensor product or is it a bilinear form?
it's actually a bilinear form and a tensor product there, kind of the same thing. Yeah, so the bilinear form, so one of the arguments comes here, one of the arguments comes here. Yeah. No, it should be from H to H.
Are you taking it as a bilinear form or a quadratic form?
A quadratic form.
Yeah, so the arguments over there are both the same, right? That's what I'm saying.
No, it's a bilinear form. You're allowed arbitrary. Yeah, yeah.
If it's a bilinear form, then it should be from H2 to H, then, or H2 to R. I mean, if you're looking at it as a form, right? Form is supposed to give an output as a scalar, not a.
Yeah, I mean, it's like a matrix you can think of as a map from Rn to Rn, right? Yeah. So this is exactly that. So if you have A, which is your PSD matrix, you have X transpose Y. This takes, so A to this is from Rn by n to R, right? But if I were to just look at A, right? This is from Rn to Rn, right? So that's what this is A, that is H.
Oh, like that means it's the sum of n rank one. Okay. So one can also think of this as a singular value decomposition happening simultaneously while one is looking at this, right?
We'll get to that in just a slide. You are on the right track. Yes, yes. Right. So this is the iteration that I would like to run, because this is much faster to run than the previous iteration. This has a much lower condition number. Okay, so if this is my operator, how do I actually track this spectral preconditioner? This is the bookkeeping task at hand now. And so the Hessian is nothing but A transpose, where A is this operator, and A transpose A, which is the dual operator of sorts, is nothing but the kernel matrix, right? And what do we know from linear algebra? The eigenvalues of this matrix and the eigenvalues of this matrix are the same, and their eigenvectors are related very nicely, right? So the eigenfunctions of my Hessian are nothing but this operator times the eigenvectors of the kernel matrix. Okay, so all I need is access to the eigenvectors of the kernel matrix, and I can implement this. Yeah.
I'm not sure, but eigenvalues I agree are equal or conjugate maybe, but eigenvectors are not always related, right?
They are, right? They're related in exactly this way, right? In exactly this way. This is the singular value decomposition.
Oh, yeah,
you multiply from the.
Not A and
Yeah, yeah.
Not A and A.
Yeah. Okay, so now I need to find out what are these eigenvectors of the kernel matrix. Once I know that, I know psi i's, and I can implement the preconditioned SGD as well, right? So here is what this looks like. The simplification of this is the following. This is my stochastic gradient, and I want to apply the preconditioner to this stochastic gradient function, right? And I now slowly go through the derivation one by one. There is the identity map, which just keeps the stochastic gradient as is, and then the correction part of this preconditioner, which essentially is psi I times the dot product of psi I with the stochastic gradient. Using this, from this step to this step, I need to apply again the reproducing property of the RKHS. That gives me this. And this now I just substitute what are psi I in terms of EI, which are my eigenvectors of the kernel matrix, and that gives me this form. And that finally tells me how what I should do to track the preconditioned SGD in my RKHS. So I run the SGD update, which is update the B coefficients corresponding to the batch. And then I have to do a correction for the preconditioning, which requires me to update all the coefficients in my. That is expensive, right? So this was the first algorithm that came out. This is not a very efficient algorithm, but when seen in the right lens, which is what we are doing now, you can actually hope to make many, many improvements in this now. Okay, so.
But by having a PV transposer over there, it should become somewhat more controlled, right?
Yeah, this is a low rank matrix, but it still requires me to update all the coefficients of the target, right? That's not nice. I'd like to do it with much lesser. I also need a memory of n times q to store this E matrix of eigenvectors, which is really expensive, and I don't want to pay that higher price as well. Okay, so the natural thing to do is now, can I precondition in a better manner in some sense? Can I have a cheaper preconditioner that is less expensive to store? And okay, before that, the biggest advantage that you have is the speed up is something like sigma 1 by sigma q plus 1, and this is exponential in q. Okay, because these kernel matrices have condition numbers that are exponential in the number of samples typically. You also get better GPU utilization because your optimal batch size goes from 1 over sigma 1 to 1 over sigma q plus 1. So you go from optimal batch size of 4 to optimal batch size of 4 million, which means that you can fully utilize your GPU now. Right? Okay, so how do you approximate the preconditioner? So instead of taking eigenvectors of the entire kernel matrix, what I'm going to do is I'm going to take a submatrix of my kernel matrix, where S is a subset of my training data. I construct the eigenvectors of this submatrix and then approximate using a similar formula that we had earlier. Okay. This is also now an element. Psi I tilde is now again an element in my RKHS. I'll construct the preconditioner using outer products of these psi I tildes. Okay, so this is going to be my new preconditioner, and we had a theorem which showed that this preconditioner basically behaves like the earlier preconditioner if the size of this subset S is logarithmic in the number of training points. Okay. And now that makes, again, I have to go through the bookkeeping exercise again. What it does is, instead of having to update all my coefficients, I only have to update coefficients corresponding to the subset that I had chosen to obtain my eigenvectors for the preconditioner. Okay. So this requires only there is no n times q memory, it's n plus q memory that you require to store this preconditioner now. And the setup time also goes down from quadratic to O of 1 in terms of the number of samples.
This subset changes a bit, right?
No, you just fix it once and you don't change it again. You just IID subsample, sample without replacement. That's it. That's good enough.
Still running on all N, but the preconditioning is only happening on N.
Correct. Or the preconditioning is actually happening in the function space. To track that approximate preconditioning, you only have to track the behavior of the coefficients on S. That's it. Yeah.
And log for 4N.
Yeah, this is some. I think that is an analytic issue. If we had been more careful and smarter in our analysis, you can probably bring it down to O of 1 as well. I think omega of 1. Yeah.
Omega of 1?
Yeah, I think you should be able to.
That one sample is enough.
No, omega 1. So like constant number of samples.
Constant number of samples.
Yes, yes, yes. Okay. Yes, so there is a dimension dependence that I'm hiding in this theorem that we had here. Yeah, the dimension dependence is not actually explicit. It's through the eigenspectrum of the kernel matrix and so on. Okay. So the standard kernel machine that you've seen so far requires O of n time at inference, n being the number of training points. You want to have the amount of resources you require at inference should be independent of how much training data you have. Right? Like otherwise, it's as bad as a lookup table, really. Right? And so the standard way of actually applying kernel machines in practice is to use what are called inducing points or knots or centers, and you use models of this form. Okay, so you have some ZIs which are centers in your domain, you may do something like a k-means clustering beforehand, and you choose some centers, and then you fit these coefficients beta I once the centers are chosen. Okay. Typically, in practice, we observe that the number of knots or centers you need to choose is much less than the training data that you have access to. Okay. This is just, we don't know why this happens, but typically you need far fewer number of samples, far fewer number of centers. But you do actually need to increase the number of centers if you get more data. Okay, because the performance of the model will saturate if you don't increase the number of centers with the number of data. So we don't quite know exactly what is the relationship between P and N, but there is some sort of a growing relationship between P and N, and hence you want to be able to train models with larger centers or larger P, right? Okay, so this is now going to be how do we train these inducing point kernel machines where the centers are chosen for us. Okay, so I'm going to assume that these centers are chosen for me, and I just want to find out what are these coefficients beta. Okay, and now this is equivalent to solving this sort of a n by p rectangular system of equations. Yeah. And again, to solve this problem, we are going to stick to this philosophy. It has served us well so far. So we are going to do the same thing. We are going to come up with algorithms that are directly in the Hilbert space and track them in finite dimensions. Okay, so the functional form now is that the function is now going to lie in the span of my basis functions, which are centered at my inducing points Zi. And the main challenge is that the gradients are still of this form. So the gradients are still going to depend on the data points and not on the centers. And so every time I take a gradient step from my constraint set, I'm going to leave the constraint set. Right? So what do I do? Projected gradient descent. Right? So this is the update I want to now track. This is one step of preconditioned stochastic gradient. And now I need to do a projection after that one step was taken. Okay, so here is a quick lemma that actually tells me how projections work in the Hilbert space. Okay, and because we are in the Hilbert space and the dynamics, the designer of the dynamics does not know any other space, so the projection also has to work with the norm that is belonging to that particular Hilbert space. So if this is the if G is a function in the Hilbert space and I want to project G onto the script Z, right, which is the span of my inducing points, then the solution is of this form where beta is nothing but the solution to this linear system of equations. Okay, k z z beta is g of z. What is this g of z? It's the evaluation of the g that I want to project at all the points in my inducing points. Okay, so here is a quick proof for why that is true. So the projection is nothing but the minimizer of the distance between f, which is in that set, and g, which is the point I want to project. Right. This I can expand as norm f square minus 2 times the dot product of f and g, and the third term is just dependent on g. I can drop that term. Yeah. Yes. And now I know that f has to be of this form, k dot z beta, right? Which means that the norm f square has this form, beta transpose k z z beta. And the dot product of f and g has this form, beta transpose g of z.
Why is k dot z transpose k dot z k z z?
So k dot x dot product k dot z. This is a function. You apply the reproduction property and you get k z x, which is equal to k x z. Right? And that basically gives me this. It also gives me this. Okay. Now that I know this, I can solve this subproblem of projection using EigenPro 2, which is the algorithm that we just saw earlier. Right. The only thing now that's different is I can choose z as my data and g of z as the targets that I want to fit the kernel machine on. Right. And so this is what this projected preconditioned stochastic gradient descent now looks like. You first calculate the residual on your mini batch of data that you get. You calculate some sort of a vector that is the evaluation of the new function that you've calculated, and you now want to project it, which means you have to solve a linear system of equations. This is what the equations look like. What's nice is now that the memory requirement is independent of n. At inference time, I do not need memory that is dependent on the number of samples. What's not so nice is the number of flops per sample during training is quadratic in the number of in centers that I have in the model. This is what makes it slow. And that p square term really is the complexity of this linear system solve. And we want to get rid of that somehow. And so, yeah, the paper that got accepted last week was about how to get rid of this. And the idea really is instead of projecting every step, you project after a few steps. So you keep tracking SGD in the function space, and then you project it after t steps, right? Because the most expensive step is the projection step. You amortize the cost of projection by waiting for a few steps of SGD before you project it, right? This just makes your life hard as somebody who's doing the bookkeeping of this. But
yeah, how do you keep those betas?
Exactly. So when you now have to do that, let's look at the example of when you want to do projection after two batches have been processed. So let's say x1, y1 was one batch and x2, y2 was the next batch. This is what the two updates look like. You take one gradient step, and then you take another gradient step, and after the second gradient step, you do a projection, right? So you need to track what is happening to this intermediate function, right? And so this is what we'll do. We'll track what exactly is the intermediate function. The intermediate function turns out is an inducing point kernel machine, but with more inducing points. So the original model had only inducing point z, but now there are going to be two more inducing points, those corresponding to the batch that you just saw, and those corresponding to the preconditioner for your training.
X1 was the batch.
X1 was the batch. XS is the preconditioner, the subset of the data you use to get your preconditioner. Okay, so you need to now track what are the coefficients of these. Okay, and we did that, and that kind of gave us this algorithm, which essentially keeps appending some sort of a temporary centers for a few steps. And at some point, you project it again. Once you project, you don't have to keep track of those temporary centers anymore. You flush it out, right? So this W is the set of temporary centers. I keep tracking W and the weights corresponding to those temporary centers. And then I flush it out after every T steps, capital T steps, right? This basically solves the problem. Now the total cost, number of flops per sample has gone down by a factor of T. Right? And I can choose T to be arbitrarily large, and we choose T to be P over B. There's no trade-off in performance. There's a trade-off in memory in some sense, because now this factor of 2 here is because you have to keep track of these extra centers that you now have.
And that is not too bad.
That's not too bad. It's like saving 2 models, right? Okay, so this makes my cost amortized. So here is a quick comparison of all the algorithms that we've seen so far. So this was the Falcon algorithm, the state of the art until 2020. And then a series of algorithms, we made small contributions in each paper. And we finally have got the numbers down to what we think are optimal. So all of these had a number of steps that you required were proportional to the condition number or the preconditioned condition number. But that is not optimal. If you choose momentum instead of momentum as well, along with your SGD, you can get to square root kappa. And that is also something we've now explored. All of this was just for the square loss. We've managed to extend it to other sort of smooth convex loss functions as well. That's a paper that we're writing currently. Well, these 4 are by me. The bottom 4. Yeah. Wherever you see a P is me. Okay. And yeah, this is also an analysis paper on the side, which tells you that the size of the subset of the data that you need to get your approximate preconditioner is log n power 4. You don't need significantly more coefficients to be updated in every step. Here are some numerical experiments. So I guess this is basically saying that as you increase the size of the model, which is the number of inducing points, the performance keeps improving. All the models roughly give you the same performance independent of what algorithm you use. And that is because they're basically solving the same optimization problem in some sense. So that's the test accuracy. But what I'm showing you here is the time it takes to actually run these algorithms. This is the Falcon algorithm, which cannot train anything beyond 128,000. It just requires too much RAM. The EigenPro 3 algorithm has a quadratic dependence on the number of inducing points, whereas EigenPro 4 has a linear dependence on the number of inducing points. So, so using speed up to describe the how fast EigenPro 4 is versus EigenPro 3 is not fair to EigenPro 4. But nonetheless, here is some more numbers that show how much faster this is. So I told you that it used to take us 10 days to train a model, and now it takes us 21 minutes to train a model. This is all on one GPU, one A100 GPU. Okay.
How's the performance compared to neural networks?
The performance comparable to neural networks is not as good yet, because this is using sort of a kernel function that is not best for the task. You need to choose a kernel function that is best suited for the task. That is a separate direction of work. There's still a lot of open questions there. This is using a suboptimal kernel, which is easy to calculate, what is called a Laplacian kernel. That's what we used for this particular set of experiments.
So why neural networks is drops in TPS kernel?
Why neural networks? Wide neural networks, exactly. Yeah. So the Laplace kernel exactly captures the same RKHS as wide, fully connected neural networks of any depth. That is why the Laplace kernel is what we use.
Can you combine these kernels with the deep learning architecture?
Yeah. So you take a pre-trained network on some data. You just pass through those pre-trained networks, get the embeddings at the output, and fit a kernel machine on that. That's almost always better than just fine-tuning the last layer of the neural network. This is exactly that.
A little question. So when you're training, like, so these conversions happens from any initial point?
Yes, because these are convex algorithms, right?
The one.
Yeah. Okay, so I guess I'm going to stop with some open questions. How should these things grow with n? These are still things we don't quite understand well. What is the dimension dependence? What is the problem dependence? How should you choose the centers? Currently, we just either do IID subset selection, or we do k-means, and then you choose those centers based on k-means. But is there something smarter that we can do? And my hunch is that you should be able to do this with omega 1, the size of the preconditioner subset being omega 1. Yeah, more long-term kind of questions that I've been thinking about for the last couple of years. There is something which is a generalization. So Hilbert spaces generalized to something called Banach spaces, where dot products are not defined, but norms are defined. Right? There is a notion that generalizes RKHS to RKBS. In fact, there are 3 different definitions for RKBS that exist, and they don't uniquely map to the same thing. But is there a class of these reproducing kernel Banach spaces on which we can do the same thing? Now, the challenge is that Frechet derivatives no longer lie in the Banach space. They lie in the dual of the Banach space. So you can't do SGD. You have to do something called stochastic mirror descent. And that becomes a headache because we haven't figured out how to track stochastic mirror descent in Banach spaces yet. If someone figures out, please let me know. There is another nice, elegant line of work which tells us that neural networks are actually the solution to a non-parametric estimation problem on a class of Banach spaces. Okay, so multi-layer perceptrons or fully connected neural networks are the optimal form for any solution to a non-parametric regression problem on a Banach space. No, with the nonlinearity. So we are now talking about the function space directly.
What about transform considering that?
I'm sure there is going to be an equivalent formulation in some more complicated Banach space, perhaps, but it's still going to be a Banach space. And the beauty of this entire approach is that we've been doing convex optimization in the function space all throughout. So these are going to be algorithms that will converge. The question is, can you now track these algorithms in the parameterization of the neural network? That is still unclear because the parameterization is no longer linear in some sense. Okay.
You want basics of this, you know where to get it.
The red book. Okay, I'm going to stop.
Okay, so informal, any questions? Any more questions? Does this connect to like tensor programs?
Maybe, I don't know. Maybe. That is some dense material I have not been able to get through cleanly yet. It would be nice if somebody makes a clean connection.
Thank you. I think we still have the team. Nice one.